Okay, I would like to say hi from Istanbul, Turkey. I'm connecting from ChairYeditepe University from Istanbul. And I would like to thank to the organization committee of Zero Build Forum 2020. And the topic is, I guess, a very meaningful topic, error for zero. I think we have a global error, I believe that. And let me introduce myself briefly. I am Associate Professor Doctor in ChairYeditepe University, Department of Architecture. I'm working as the Vice Dean of Faculty of Architecture. And in our university, we have a sustainability working group. And in our research areas, we include zero energy buildings and very many interdisciplinary sustainable and energy-based researches. So I would like to thank to the organization committee for inviting me here. It's my honor. And I would like to tell that this session is a real international session. We have three distinguished speakers, invited speakers from 3 different countries and cities. So I believe it will be a very rich and we will hear different approaches from different countries. So our session number is 222, and the topic of this session is the case studies delivering net zero buildings. And we have 3 invited speakers. Let me introduce them briefly to you, then we're going to proceed with the first speaker. The first speaker is from United Kingdom, Kirsten Henson. She's the director of KLA Sustainability, and the topic of her presentation is Delivering Net Zero Homes, a Case Study, Orford Mews. Welcome, Kirsten. Nice to see you here. And our next, the second invited speaker is Professor Ambrose Dodoo. He is connecting from Sweden. And he's a professor in building technology in Linnaeus University. And the topic of his presentation is Transition Pathways to Zero Energy Buildings, Experiences in Implementation of Zero Energy Building Solutions in Sweden. We're looking forward to hear you. And the last speaker is Professor Ludwig Rongen from Germany. And he's the founder of ROA Rongen Architects. And the topic of his speech will be World's Biggest Passive House Project, Harbin in Northern China. Welcome to you all, and I would like to say welcome to the all audiences. I'm going to give another information about our session. The maximum time limit of our session is 70 minutes. So each presentation will end in 20 minutes, and then we're going to have the Q&A, question and answer session. And please ask your questions through the chat room. So I'm going to ask your questions to the speakers after all presentations will end up. Okay, let's start with our first speaker, Kirsten Henson. I'm sorry if I pronounce your name well, I don't know. Kirsten Henson, you're the first speaker. The virtual stage is yours. I'm giving the word to you. Okay, we're looking to hear your presentation. Thank you.
Thank you. There seems to be a problem with this screen share. I don't know whether it's flashing your end.
Yes, it is flashing.
It's okay. We're here. Thank you very much, and thank you for the invitation. I will be presenting a case study that is received planning consent in the UK in London, and we're just finalising the design and about to start construction. So I'm going to take you through the case study today. I think the first thing to talk about really is how we define carbon neutral or net zero. And in the UK, London is seen as the city that is sort of pioneering the direction of net zero carbon. But what we see in the future London plan that's coming out, we talk only about regulated emissions, and those are the emissions that are controlled through planning policy in the UK, something we call Part L. And that only deals with space heating, water heating, lighting and cooling. And you'll see that there's a problem with that in terms of moving towards true net zero. And what the London plan, the second problem with the way that we sort of talk about carbon neutral or define carbon neutral in conventional planning policy in the UK, is not just we talk about the regulated emissions, but what you'll see here is that the planning policy requires us to deliver a 10% reduction through energy efficient measures, then 25% additional reduction through on-site renewable energy generation, and we can simply pay just £60 a tonne per tonne of CO2 per year for a 40-year period to offset the residual regulated emissions. So there's real issues with this. If we have a look at the next graph here, you'll see that the regulated emissions, this is what some people are calling carbon neutral, even with this offset. Heating, lighting, cooling and hot water. Some people are starting to talk about net zero being full operational emissions. So this is in the UK what we call unregulated emissions, the red bar here. And that's what we would say plug-in power. So that's my washing machine, my dishwasher, my computers. And of course, in a household, it can be quite significant. And this is the sort of contribution that you're seeing. It probably increases the energy demand of the household by about 25% if we take it into consideration. Now, of course, that's not the full picture when we're talking about zero carbon. We do need to look also at the embodied carbon of the construction materials that we are using. So the manufacture, the delivery, the installation of those building materials, maintenance during their life, replacement potentially, and then of course the end of life disposal. This is all part of the carbon footprint, the full life cycle carbon footprint. So when our client Ben Spencer from GS8 came into our office, he said to us, I want to deliver zero carbon homes. Our first starting point with him was, well, what do you mean by zero carbon? And we went through this discussion. And Ben, being a very ambitious client, said, well, I want to do whole life cycle carbon neutral. Interestingly, he already had a design. The designers were early stage 3. So that's sort of a concept design in the design stages that we use in the UK. So we were already working with something. So our first port of call was to sort of have this conversation with Ben, explore what we need to do around defining carbon neutral. And the thing is, some people get distracted by renewable energy technology, but what we fundamentally must do is reduce. It's the first step. We've got to reduce our energy consumption in the first place. There's no way that we can install sufficient renewable energy capacity if we don't significantly reduce our consumption in the first step. In order for us then to look at generating sufficient renewable energy on site to meet the demands, we need to be looking at all electric buildings. We need to be moving away from gas. We generally use gas for heating hot water in the UK. We need to move away from the use of gas. And at the moment as well, from what you'll see, we tend to rely on the electricity grid. We export our excess renewable energy to the electricity grid, and we import, for example, at night, if we have PV panels, we need to import energy from the grid. And this is only going to work for a certain amount of time before we really start having to look at renewable energy storage. So whether that's hot water storage, whether it's battery storage, localized storage. Otherwise, the energy grid is simply going to fall over with these peaks and troughs. But at the moment, we look at zero carbon as on a net annual basis. We generate sufficient energy within our building footprint to meet our building demands, but over an annual and daily life cycle. With the embodied carbon, again, the first step is to reduce all of these materials that we're using, obviously produce carbon. And once we've looked at low carbon technologies, low carbon materials, we're actually now exploring also this idea of using landscape within the buildings and in the environment to absorb an equivalent quantity of carbon that's released through the construction. So where do we start with Orford Mews? This was the site. It's just a small development, 10 homes and a small office block, workspace. And this is quite normal, if you like, in the UK. We look at small infill sites, specifically in sort of city areas. And what you'll see here is surrounding houses. These are the sort of Victorian terraces. People love them because they've got these big back gardens that you see here. But at the end, you tend to get these rather rundown garages that are underutilised. But you can see this was the site that we were looking at, an infill behind the properties here, well spaced from the properties. And of course, you've got an access in just alongside as well. So the initial design, as I say, the architects had already started work. We had the imagery that you can see here. It's quite complex, single story, part 2 story. You can see that there's a lot of movement in the facade in terms of setbacks, corners. We have some very complex junctions here. You see a glazing to glazing junction. We were looking at glazing ratios of 32% with large south-facing windows. Part L compliant U values, so that's where regulations will take us. They're those regulated emissions. It tells us what U values building fabrics must achieve. At this early design stage, no mechanical and electrical, and there was rooftop PVs on the west-facing roof. When we did the analysis, we found that the estimated operational carbon was about 109 kilowatt hours per metre squared. Having a look at the embodied carbon here, we had, again, quite traditional, I guess. Okay, we're not using brick in the UK. We traditionally build homes out of brick, but a concrete strip foundation. The architects tend to like open plan living spaces, and that led us to having a lightweight steel frame within the building, the PUR insulation materials, aluminium roofs on the buildings. The homes had timber facades that you see here, but the workspace actually had an aluminium facade proposed. And the estimated embodied carbon, when we calculated that, was almost 1,000 kilograms of CO2 per metre squared. So really quite significant. So once we got involved with a great design team, it has to be said, the engineers and the architects really embraced this idea of carbon neutral and really engaged with us in looking at what they could do to reduce the operational carbon. And we started these discussions around building fabric. We did some analysis of how you could improve the building fabric and what difference that would make, what the impact of different mechanical services, the air tightness, so the build quality and the design details of the building form factor itself, and some of the glazing ratios as well. So we did some early stage analysis to engage the architects in understanding the implication of the design and the opportunities that existed by rationalising the design. And what you can see here is the design development. You'll see the north facade here. We've got smaller windows, so smaller heat loss, less heat loss through the north facade, more rationalised south facade in terms of the glazing. It allows good daylight, but it reduces the risk of overheating in the summer, whilst also giving good thermal performance. You'll see that the form factor of the buildings is much simplified. We see less movement in the facade. We've got rid of a lot of those complex connections and joints. There's also been a move to improve the building U values, so having a look at the actual build-up of the external walls, the roofs and the foundation design, the specification of the windows to make sure that they are better than minimum standards. Then, of course, we have a look at the mechanical and electrical systems. Within this development, we're proposing a communal heating with an air source heat pump. So remember what I said, moving away from gas and going to all electric solutions. And the nice thing about the air source heat pump is that as we do suffer under global warming and our climate gets warmer and warmer and warmer, of course, in the summer, the heat pumps can just be operated in reverse and operate as air conditioning. So providing heating in the winter and air conditioning in the summer. Although hopefully with our design detailing and our intelligent specification with some shading, we shouldn't need heating in those summer months unless we have a very warm heat wave. We've got mechanical ventilation with heat recovery, although the windows do open. Everybody likes to be able to get some fresh air into their homes. LED lighting throughout. On-demand hot water in kitchen, so rather than boiling a kettle, you just take the hot water you need each time for your cup of tea. And then, of course, A+++ rated kitchen appliances will be provided with the buildings. So that has delivered almost a 50% reduction in the operational carbon, bringing us down to 58 kilowatt hours per metre squared. The other great thing then, of course, we looked at PV panels on the roof. And what you'll see here is a really nice design quirk, I think, in that we've simplified the building form, but the architects have then twisted the roof to allow maximum south-facing roof. So the optimum orientation and the optimum angle for the PV panels to maximize the output from the PV panels that we're putting on the roof. And also it adds this design interest. And you'll see the building at the end. This is the office space. So you're seeing the PV panels there on the roof as well. Some small green roofs and terraces cropping in on the roof spaces. That has brought us right down to just 15 kilowatt hours per metre squared. So we're not quite zero carbon yet. We've got some more considerations to look through. We're looking at smart technical solutions, on-site monitoring, having a look at how we can create an app that the residents use to monitor and evaluate their own energy consumption, and an owner engagement. You know, it's not just a case of selling these buildings and walking away. We do need to engage the residents in how they're using their buildings and see whether through those smart tech, through engagement, we can't get this now down to a net zero carbon operational resident. If we have a look at the embodied carbon, we did an analysis. I'm just going to go quickly, for those that aren't familiar, it is European standards. I think we have a lot of Europeans on the line, as it were. This module A, B and C refers to European standards, where the module A is very much about the extraction and manufacture of the building product. The module B is any replacement. So, for example, a building may last 60 years, but your chances are you'll have to replace mechanical systems. Maybe in 20 years, windows, perhaps you replace every 20 years. So that looks at replacements. And module C is what happens end of life, so the disposal impact. And what you'll notice here, by doing this analysis, the frame, that lightweight steel frame, had a significant impact in terms of its embodied carbon. The substructure, again, concrete and steel are the two biggest hitters. Each one of those is responsible for around 6 to 8% global CO2 emissions. So we need to be using less concrete and less steel if we want to move towards zero carbon. The external walls and claddings, you can see here, that aluminium cladding that was on the office building is completely offset any carbon sequestration coming through the cladding from the residences. So that really needed challenging. And that plastic-based insulation, the PUR insulation, although with a great U value, has a significant embodied carbon and contributes quite significantly to the carbon footprint of the whole life cycle. And then these internal finishes. The interesting thing here you'll see is that module A is very small, but actually because we're replacing them over the life cycle of the building, internal finishes, we're repainting, we're redecorating. That module B, the replacement, becomes really quite significant. So we started here. This is the analysis that we did to engage with the engineers and the architects to have a look at some of the design solutions. What you'll see, the engineers suggested that if we reduced the 8-metre internal span in the living areas to 4 metres, that would allow us to have a locally sourced softwood timber frame. The existing garages, we realised, the engineers said, well, we can reclaim some bricks. We can perhaps use that for commercial space cladding, but we can also use those reclaimed bricks in foundations. So move away from a lot of concrete in the foundations, reduce the amount of concrete in the foundations by actually using salvaged bricks from site. You'll see we've started exploring with some innovative materials. So this was actually done on site. This is some of my team with some experts building true rammed earth walls. There is no cement in these walls. People often talk about rammed earth, but they put so much cement in them, they really can't be considered rammed earth. This is literally nothing but the earth that we have on site. And you can see that there's sufficient clay in there that we're producing a really quite beautiful architectural internal wall, which means that there's no finishes required. That would be the finished building provides thermal mass within your residence as well. We've moved away from those traditional building materials. The aluminium on the aluminium facade on the office building here, you can see, is replaced with brick, locally produced in the UK, much lower embodied carbon. You can also see sort of planting going on around outside. We've moved away from the plastic PUR insulation to sheep's wool insulation. We're looking, instead of plasterboard, at wood fibre boards, clay plasters. So really those natural finishes, natural materials. And you can see that through those initiatives, we've managed to reduce the embodied carbon, the life cycle embodied carbon, by 65%. So we're looking at around 360 kilograms CO2. Of course, now we're sort of saying, well, what can we do to increase the sequestration, the carbon sequestration through planting on the site? You'll see we've got the north-facing roofs are moss. We've been informed by ecologists that those sort of moss plantings absorb the most carbon of any sort of lightweight green roofs, if you like. The commercial unit now has low maintenance green planting. So that's sort of ivies and those sorts of things. We don't want anything that needs a lot of maintenance, that requires a lot of water. And we've got these wonderful private and community green space. So you can see this is a sort of the communal area, if you like. We haven't yet gone through the exercise of estimating the embodied carbon of landscape and planting, and that very much is a new science at the moment in terms of carbon. So we're working through it. We're working with researchers in the area to understand how we might be able to quantify that sequestered carbon. And just sort of a note on actually the broader idea of sustainability. It's not just an office space, we've decided. Actually, we need a community well-being space so the kids can get together and have a birthday party. You can invite your neighbours round to do some yoga together. You could have a dinner party. So providing that flexibility, providing that space. And I think as we are suffering with the COVID and the lockdowns with COVID, we all know that the COVID crisis has caused a mental health crisis. And I think these protective spaces within our community are going to be really, really important as we are facing more and more of these sorts of challenges, whereby people can still protect themselves, but don't have to completely lock themselves off from social contact, because it's really quite damaging. We'll see here that we've got cycle parking facilities. There's only going to be direct car access for one disabled parking space. That's it. It's very well serviced by public transport. We're going to have a reuse station. So the idea is not everybody needs to buy a ladder or a hammer or a drill if they want to put up a shelf. They can simply go to the community reuse station and borrow those materials. So we're moving towards this idea of a sharing economy, a sharing room, composting facilities provided on site so that people can use that community area for growing vegetables, providing a bit of resilience, if you like, in terms of the community food provision as well. So we do still have some work to do. This shows you the red bar is the operational carbon, the cumulative. You can see that very small increase as we go. The grid in the UK, as with many electricity grids across the globe, is decarbonising. So we have taken that into account. But we still, as we say, we even with all of these initiatives and these ideas, we still have a little way to go to deliver true zero carbon. What you can see here is the negative embodied carbon of construction, and that's because of all those natural materials we're using. The clay, very low embodied carbon, but the timber, straw, those sorts of materials sequester carbon in their growth period, so they become negative. There is something very strange with carbon footprinting and the way that we have to undertake life cycle carbon footprinting, the methodologies that we use in the UK, that says that all of that carbon that we've sequestered in those natural building materials has to be released into the atmosphere at the end of life. So even if we reuse those building materials rather than burn them, for example, the timber, we still have to reuse it, release that embodied carbon. My feeling is that we face a carbon crisis now. So, let's take advantage of natural building materials that that absorb carbon in their growth, rather than using concrete steels that release carbon when they're manufactured, and we can continue as we move towards this low carbon economy. The fact that we may burn for biomass the timber afterwards, I think, we're moving that down the line. It's not that we're shifting the problem down the line, but we face a carbon crisis now. So let's move towards low embodied carbon materials. So in terms of repeating success, I think there's a few key things we need. There's a strong client vision. You need to ensure that there's a clear definition of net zero carbon that's understood by the whole design team before you start. There's a willingness within the design team to include sustainability as a key design driver. We often look at cost and program and sort of the architectural wow as design drivers, but actually sustainability has to be a key design driver in order to progress towards zero carbon. And the designers have to understand that and think within those sort of sustainability parameters, if you like. Collaborative design, where everybody is open to ideas. No idea is shut down before it's explored properly from a cost, program, architectural, engineering perspective. It's an iterative process. We can't get this right first time. So there is time required for thought, time required for analysis, to go back and do the technical analysis and see how far we've got. Exploring innovation with the supply chain is a really important part of delivering zero carbon buildings. And of course, trialing new products as well. We can't be afraid to sort of try some of those new products. So that was a really swift introduction into a case study that we've been working on. And I will hand over, I believe, back to the studio, as it were.
Thank you, Kirsten. It was a great presentation in that short time. I know it's a twist presentation. Challenge. It's another challenge, but I would like to emphasize reduce. I saw that you wrote with capital letters reduce more than 2 times, and that means that this is the overall concern of your presentation. And as an architect, I really found this infill project, which is a very contemporary approach. It seems that you had a real teamwork behind this project. It's obvious. And I found the twisting roof decision very creative, both in terms of design, because it makes the roof very dynamic, and also in terms of sustainability, because you're trying to catch up the optimum the sunshine. And then in this case, your example, your case proves a whole design process should be done for a real sustainable project. So thank you very much for your great presentation. I am going directly to the second invited speaker, Professor Ambrose Dodoo. The virtual stage is yours. We're looking forward to hear your presentation. Thank you. However, Ambrose, I cannot hear you. I guess the other audience cannot too. Can you test your voice once more? No, I cannot hear. I guess no one is able to hear you. I see your microphone is on, but I cannot hear you. No. Ambrose, there is a note from event organization group. Please give permission from cam microphone button below. Did you give that permission?
Yes.
Now we can hear you. Perfect. Okay.
Okay. Please, can you see my screen also?
Yes, we do.
Okay. So I start. Thank you very much, all of you, and for the opportunity, to present my thinking and my research on nearly zero energy building. As it has been said, my presentation is on transition pathways to zero energy buildings. And over here, I'm going to talk about the recent project on nearly zero energy building in Sweden. So let's start with a global picture. Globally, our society is heavily dependent on fossil fuels, as we know today. More than 80% of all the energy globally is coming from fossil fuels, and the projection for the future shows that this trend is likely to continue. Now, as we use more energy, we are also trying to achieve less carbon, and this doesn't go so well. If we want to achieve the target of the Paris Agreement, then we have to immediately start reducing our carbon dioxide emission. And by the middle of the century, we have to about halve that or reduce that about 50%. Now, for us to reduce energy use in our society, we have to understand where we use the energy and the dynamics in these sectors. And if we look at our sectors, we can see that the building sector is one of the sectors which uses the largest share of the energy. Apart from the industrial sector. Today, 1/3 of all our energy is used in the building sector. We can see that the annual growth of energy in our sectors has reduced slightly because we are pursuing more energy efficiency measures. But still, the energy used in the building sector is significant. This is a global picture. We can also see the same picture from the European perspective, where we see that the building sector accounts for most of the energy use. So we have a lot of potential in the building sector because this is a sector we use a lot of energy, both globally and in the European Union. One of the things we have to think about is the cost of reducing carbon. Is it cost effective to reduce energy use in the building sector if there is a lot of potential? And this greenhouse gas abatement cost curve gives us a picture about the cost of reducing CO2 in different sectors of our society. And we can see the negative cost means benefit. When cost is negative, it means we benefit because we save more compared to what we invest into the measure. And when the cost is positive, it means we pay. And if you look at the cost over here, we can see that the residential sector or the building sector gives some of the lowest cost of reducing carbon dioxide emission in our built environment. For instance, we see residential appliances over here. We see residential retrofit of heating, ventilation, and air conditioning systems here. We see energy efficient buildings. We see insulating buildings. These are all negative costs. So apart from the fact that we have large potentials to reduce energy use in the building sector, the cost of reducing CO2 emission in the sector is also very low. So this gives us motivation to pursue efforts to reduce energy use in the built environment or in our building sector. There are many measures we can implement in the building sector. And today, what the European Union is advocating for more and more is transition to nearly zero energy buildings. That is, buildings with low energy use and the use of renewable, on-site renewable technologies. This is how the European Union defines nearly zero energy buildings. And so in the NERO project, we have partners from 4 Nordic countries or Northern European countries, including from Finland. We have Kovla Innovations from Finland. We have Aalto University, also from Finland. We have Tallinn University of Technology from Estonia. Then we have Växjö Kommun, that is in Sweden. Linnaeus University also in Sweden. We have Sintef in Norway. And yeah, so these are the partners of the project. And this project is financed by the European Union to explore strategies to create nearly zero energy buildings with wood frame. Because as Kirsten showed, building with wood results in less carbon emission or embodied carbon emission compared to building with non-wood materials, which I will also show in this presentation. So, in brief, the NERO project develops and demonstrates technical solutions which significantly reduce the cost of nearly zero energy wood buildings. And the project look at three main aspects. We have the technical aspect where we look at reference buildings and case study solutions. For instance, what kind of insulation, what kind of measures can we implement to achieve nearly zero energy buildings? We also look at the financial aspect, that is the cost effectiveness of the measures, and also the procurement models to implement these measures. And lastly, we also look at environmental aspects of these nearly zero energy buildings. That is, we look at life cycle impacts of these buildings in terms of embodied carbon and embodied primary energy use, and also indoor climate conditions. So these are some of the buildings which were studied in the project in Växjö. As I said, we have project partners from 3 other Nordic countries, but in Växjö in Sweden, these are the buildings which were studied. And as you can see, most of these buildings are wood frame buildings. Of course, we have a concrete frame building over here, but most of these buildings were built with wood frame, and just recently. And we can see some of the construction details of these buildings. For instance, we see the U values of the building elements. They are quite low compared to what the building code requires today. For instance, we can look at the U value of the windows. That is 0.9 watt per meter squared Kelvin. And this is about the best on the market today. We can also look at the infiltration rate or the air tightness of the buildings. And this is about 0.3. And this is, of course, the minimum level required by the passive house stand, for instance. So the buildings which we studied in this project are quite energy efficient compared to what is required by the building code. And what we have done in this project is to look at the calculated and the measured energy performance of the buildings. And we can see, for instance, we have the Arkan building in Växjö, Passet and Valen. We can see that the energy use of the building, that is the space heating, ventilation, electricity, that is the electricity to drive the ventilation fans and pumps, domestic water, and then the property electricity, that is for facility management, are quite low compared to what is required by the building code today. Today, the building code requires about 90 kilowatt per meter squared for a standard building in Växjö. But we can see that all the buildings which were studied had a lower delivered energy use compared to what the building code required. Of course, one of the challenges we faced in this project was the difference between how the building was designed and how it performed. If you look at the monitored and the calculated, we see some variant or variations between them, ranging from about 8 to about 17%. And this is a usual problem that we often design buildings, and when we calculate them and measure them, we see differences because of people's behavior of occupants, and also sometimes challenges with operating the technical systems for the building. These are the details of the energy performance. What I would like to say here is that if we look at this figure, which shows the total delivered energy use, this shows the detail, and we can see that the detail is dominated by the energy for space heating. So space heating is a dominant energy demand for the buildings, and this is not surprising as we are dealing with the Northern European climate, where it is much colder compared to other parts of Europe, for instance. And we have also done life cycle analysis of the buildings to see how they perform from embodied energy and embodied carbon perspective. And as Kirsten showed, we have used the European standard, the EN 15978, and we have only focused on the product and the construction stage of the building. And we see the models A1 to A5 for the buildings. We have not looked at the use stage, end of life stage, and the potential benefits, which if we also look at, we see that the wood has more advantage, for instance. But in this project, we have only focused on the project and the product at the construction stage. And these are the analyzed buildings. So we have one of the case study buildings for the project, a recently built concrete frame building, a 6-story concrete frame building. And in this project, we have worked with architects, and the construction company to design the same building, the building to give the same service with wood frame, with using cross-laminated timber and also with light timber models. And we have done the life cycle analysis to compare what is the implication of building the same building with concrete and the same with wood from a life cycle perspective. Of course, looking at model A1 to A5. So over here, we see the mass of materials in the different buildings. And in the concrete frame building, we see that the mass of material is dominated heavily by concrete. And when you look at the timber buildings, that is a cross-laminated timber building, that's the CLT building and the modular timber building, we also see that we have significant amount of concrete that is for the foundation and also for stability reasons. But we can also see that the use of plasterboard and also CLT is also quite significant in this building, and also lumber. So these are the mass of the materials. And then if you look at the embodied energy use, that is the energy for production for model A1 to A5. So we have raw material extraction, transport, we have we have raw material extraction, transport, assembly of the buildings, all of them together. We see that the concrete frame building uses much more embodied energy or primary energy use compared to the timber buildings we can see over here. It takes more energy to construct the concrete building because we need heavy equipment to move these prefab concrete elements compared to a timber building. And also, if you also look at the material, energy to produce the material, we have a lot of concrete and also reinforcement in the concrete building. And this results in much more embodied energy use or primary energy use for production. And then this is also a similar figure, but for the carbon footprint, that is embodied carbon. And we can see that the carbon for emission for the concrete frame building is about twice that of the wood frame building. So building with wood results in less carbon dioxide emission compared to concrete, as Kirsten has also emphasized in the presentation. And over here, we see the details of the different flows. For instance, we have the material production carbon emission, we have the building construction, and also we have the cement reaction. And the cement reaction is the carbon dioxide emission, which is released during the production of cement from the calcination process. One of the raw materials for production of cement is limestone. This is the biggest raw material. And you have to break down the limestone, or you have to heat that to break down into clinker. So when the limestone breaks down to clinker, that is calcium oxide, carbon dioxide is released, and this is a chemical reaction. So this does not come from fossil fuels, and we can see that this is also quite significant. And we have also done economic analysis to show the cost effectiveness of the solution. And we have dealt with different issues. For instance, when we are doing this kind of cost analysis, where is our reference, or which building should we use as our reference? Because if you want to develop zero energy building or nearly zero energy building, and you want to see whether they are cost effective or not, we have to compare them from somewhere, or we have to start from somewhere. What should be our reference? Should it be the minimum requirement of the building code, or for instance, should it be existing buildings which are less efficient compared to today's building code? The next issue is the actual solutions. What kind of solutions can we implement to achieve nearly zero energy buildings in terms of windows, in terms of insulation, in terms of ventilation systems? Another important question is also the service life of the meshes. How long are the meshes going to last? This also influences the cost, because if we have to replace the meshes several times, it means the cost is going to increase. But if the meshes last longer for the lifespan of the building, that means it makes them more cost effective. Another important parameter in this kind of analysis is the time span of the analysis. What time span are we looking at? Are we looking at 30 years, 50 years, 100 years? Obviously, this has implication for the cost effectiveness and also the real discount rate. How are we going to discount our investment? This is very, very important, as we'll see in the subsequent slide. And also, how is the development of energy price with time? Is it going to remain constant, or is it going to change? Of course, energy price changes with time, and this also has impact on this kind of analysis. And these are some of the data we have used for analysis, or some of the data and assumptions. For instance, we have used a 50 years time span for analysis, and we have used the energy price in the Swedish city of Växjö, where the buildings are located, and these are the prices. And we have used a double-stage optimization method we have developed for this kind of analysis, which I wouldn't go so much into because of time constraint, but the reference for this kind of method is given in the slide. So when we do this kind of cost analysis, we come out with how much thickness of insulation, what type of windows we should use if we want to achieve nearly zero energy building, for instance. And we see the kind of thickness of insulation we need for the ground, for the roof, for the exterior wall, and for the windows for us to achieve nearly zero energy building solution. And we have also done cost optimal analysis. I mean, what is cost optimal? Obviously, what can give us nearly zero energy building is different from what can be cost optimal. So we have done this analysis looking at different discount rate and looking at different energy price increase. So for the business as usual, we have used, for instance, a discount rate of 5%, which is typically used by businesses today. And we have the intermediate, that is the middle scenario, where we have assumed a real discount rate of 3%. And then we have the sustainability scenario, where the real discount rate is 1%, for instance, to encourage investment in energy efficiency measures or for companies to borrow money to implement this kind of measures. And what we can see is that when we implement the nearly zero energy building solutions, the space heating demand of the building is reduced quite a lot. That is where we get the lowest space heating demand of the building. That is an obvious fact. And this is a reference building. This is the building we analyzed. The space heating demand is about 51. But when you implement all the measures which we found for nearly zero energy building through our analysis, then we about half that. So we can see that space heating use reduced quite significantly. The next thing is the cost effectiveness of the measures. We can reduce space heating a lot, but as we can see over here, when we implement nearly zero energy building, of course, we get some cost benefit depending on the kind of how we discount our investment. But we can see that this is the kind of benefit we get is very less compared to, for instance, when we have cost optimal solutions. For instance, when we have low discount rate, that is under sustainability scenario. So in conclusion, I will say that the building sector uses a large share of our society's energy use today, and nearly zero energy buildings are crucial for transition to a sustainable energy future. And nearly zero energy building solutions give large reduction in delivered energy use from the buildings we have studied in this project. And we also found that cost optimal solutions give bigger financial benefit than nearly zero energy building solutions. So even though we get large energy savings from nearly zero energy building solutions, we have to do something about the cost. We have to do something to make the cost come lower. For instance, the government should intervene in this kind of things. We should not just leave the market to operate by itself. And what we also found was that the real discount rate is very, very important to make nearly zero energy building cost effective. If we have a very low discount rate, it will encourage investment into energy efficiency measures. And lastly, wood-based building give lower life cycle impact than concrete-based building. Thank you very much.
Dear Ambrose, I would like to thank you for your timing. It was perfect. You're on time.
Thank you very much.
Thank you very much.
Thank you.
And in your presentation, we heard about global energy and carbon emission trends and the cost of reducing greenhouse gas emissions. And I noted down some dramatic data in energy performance in some analyzed buildings. And in the last, you emphasized the economic analysis, which is the most discussed area of energy efficient buildings and some optimization methods for cost effectiveness. Thank you for your great presentation. Maybe the audiences may have some questions in the end. So let's wait for the Q&A session. Thank you very much once more. Now our last speaker is ready, Professor Ludwig Rongen. I'm going to give word to Professor Ludwig. Welcome to our session once more, dear Ludwig. Please open your microphone and share your screen. Ludwig, we cannot hear you. Can you please first open your microphone?
Open my microphone.
Thank you.
Does not work.
We can hear you now. And please click on share screen.
Yes.
And then click entire screen again after that.
I click on share screen, but it does not work. Why not?
Now we cannot see your screen yet.
Yeah. I go to my expert. He can do it. Give me some minutes.
Okay. Also, may I ask to the technical team, do you have his presentation? Can we share the presentation? Okay, let's try this way.
So I'm here. I'm back. Und schau mal.
Dear Ludwig,
Yeah.
the technical team has your presentation, so maybe they can share the screen. Can we wait for their attempt first?
Yes.
Okay.
So, jetzt kann ich gar nichts mehr sehen. Can you hear me?
Yes, we can. Yes.
But I can see you.
Okay, please, Kirsten, the technical team is ready to share. Ludwig, you can only talk. They can share the screen now. They have your presentation. We're waiting for the presentation now. Yes, we can see the screen. Yes, okay. Dear Ludwig, I would like to tell one more thing. Our session will end up in 25 minutes. So please try to sum up in 20 minutes because the other session, live session, will start right after ours, so we cannot have too much extension, okay? Thank you.
Okay, but I can't see. Guck mal, ich kann das jetzt nicht sehen.
We can see. Can you see it? Okay. No?
Yeah. No, I can.
Okay.
No, I can see. Yes, thank you.
Thank you very much.
It's already here. Yes. Okay, but it's not the first slide which I see here. Ah, thank you. So, I can start.
Please.
Yes.
Yes, please.
Do you hear me? Okay, thank you. Okay, good morning. Good afternoon. Thanks so much for invitation. It's an honor for me, also for me, to speak at Zero Build 20. These slides, I will not waste time with these slides. We all mix experience of climate impact, and we know that, but I cannot find the next slide. Can I do it by myself? No. That seems to be a problem. Why is it not possible? Yeah, but I would.
Dear Ludwig, can you hear me? Okay,
yes, I can hear you, but I cannot.
Mrs. Gökşen is controlling your presentation. Maybe you may say her next, okay? Then she can proceed to go to other slides, okay?
Okay, I shall. Okay, I will always say next. Yes, okay. Thank you. Then please let's start again. Okay, these slides show us our experience, which we daily make. We can't reduce. We cannot stop the climate impact. I think we can only reduce or delay it. Next. Next, please. Next. Also, these slides are our daily experience. Meanwhile, next. We have to reduce energy consumption to minimize CO2 emissions into the atmosphere. The passive house is a worldwide acknowledged highest standard energy saving building. But next, we have also to think about renewable energies. We should supply our buildings to 100% with renewables. Next. In 2010 already, all European countries decided to allow only nearly zero energy buildings from 2019 for all public buildings, from 2021 for all types of buildings. But we all know that we did not reach that goal. For me, it's also very important that we should produce the renewables at the site where we need it. Next. There are much more requirements for sustainability in buildings. We have also to think about sustainable water and waste management. We have to avoid waste. We have to avoid water resource. We have to also to save our water, our drinking water. We have to use recyclable materials and so also ecological sound materials. And we have also to implement corporate strategies for social commitment. Next. And for me, it's also important how can we reach the good values. It's very important to avoid hazardous waste. Otherwise, the society would ask architects, as architects in the future, why did you destroy our environment? Why did you use toxic materials? Next. And by using recyclable materials, we can also give back the resources to the life cycles. Cradle to cradle, that's what we should do. And so we can avoid unnecessary waste. And so we can also protect the resources. Next. High quality in architecture. I say architecture. Architecture is not only high quality in design. There are a lot of requirements, but it's also not only high energy efficient too. Next. In the past, not particularly talented architects discovered the passive house as a potential business model that will result in building culture losses step by step if the construction standard is significantly influenced by architects who does not feel responsible towards building culture or do not have modest design skills. And if worldwide acknowledged architects or passive house proponents argue high aesthetical claims result in increased costs for which a passive house standard could be made responsible, that is also a problem which could result in losses of building culture. Design is not only a question of beauty, design is also a question of, in that case, what you see here, increasing the capacity and concurrently reducing the energy consumption. Next. In the case of that building, we waived movable sun protection because movable electric sun protection use energy, and we want to reduce energy consumption. In that case, the overhanging second floor shadows the total glazed ground floor, and so we have a huge solar gain in the winter time and a shadow living room in the summer. And the water basin in the front is for pre-cooling the facade, the glazed facade, because in the summertime the wind flows over that water area and by vaporization, we cool down the facade by around 4 to 5 Kelvin. Next. In that case, in the case of that psychiatric clinic in Cologne, we designed a clinker brick facade. For the client, it was very important to supply that building to 100% with renewables. Next. And for that, we thought about deep drilling, but deep drilling was impermissible because of the water protected area in which our site was. Next. So we thought about other options, and our idea was using geothermal compound curves in a deepness of about 4 meters under the ground. But it was not enough. We had an area for only, the plot area was only big enough for around 6 compound curves, but we needed more, but it was not possible. So we decided to collect the rainwater in a leaching basin. The water sweeps away into the ground directly above the compound curves, and so it was possible to bring the building and that clinic about over the winter time by renewable, by collecting the rainwater and sweeping away into the ground. It was possible to recharge the temperature, the warmness in the ground better and more, and so we could gain enough energy from the ground to bring that building over the winter time only by renewable energies. Next. That's a finished building. Next. In the case of Z plus energy building, we used up an ice storage. Next. And by using an underground ice storage, we storage the warmness, the heat from the summer in a concrete storage under the ground without thermal insulation. It was not necessary to use thermal insulation. And in the winter time, we produced ice by contracting the warmness out of the ice storage. We produce ice, and with we can cool that building, the rooms, during the summertime. So we move the energy from time to time. In the winter, we use the warmness. In the summer, we use the ice. Next. So it is here the same. Using a heat pump, we use the heat pump for heating and cooling. And in the summer, the coolness came from the ice. In the winter time, the warmness came from the water. Next. Here we can see the ice storage in operation. Next. And we used all the solar air collectors as horizontal absorb solar energy collectors. These collectors provide a large area in the vertical to gain energy contained out of the ambient air, even if the sun is not shining. Next. We also built in combination with the flats an indoor riding hall, so we could also use the warmness of the houses for heat recovery. Next. Daylight is also important in the case of energy saving. We our intention was to reduce the electric power for lighting. So we designed a subterranean garage which is supplied with daylight. And in addition to these sustainable effects, we also implemented a grey water installation recycling system. The wastewater from the showers, the washing basins, the washing machines, and so on is recycled, and the rainwater we use it for the ice storage and also for the closet flushing. Next. And each apartment, each flat has its own recharger for electric cars. Next. You can see that this is not a normal standard building. It's a building in a very high standard. Next. But for the renters who have free use of the indoor arena, riding area, and also their free charging of electric vehicles, there is not any longer utilities statements. There are no utility statements. The gross rent, including all incidental costs, are 10 euros per square meter. Next. Another project, together with Passivhaus Institute Wolfgang Feist in Darmstadt, we made a research project to develop Passivhaus for 5 different climates. There were Dubai, very hot and humid, Las Vegas, a desert climate, Yekaterinburg in north of Russia, a very, very cool climate, Shanghai and Tokyo. The most complicated was the building for Dubai. Next. From the beginning of the design, we have to think energy efficient. Because of that, only white color for the facade was the solution, because white color does not absorb the heat of the sun gain. Next. And we also decided for an inner courtyard to create a microclimate. In the inner courtyard, we also implemented water areas and also plants for the microclimate to reduce the temperature. And we brought the first floor in the subterranean, in the underground, to reduce sun gain from the outside. And there we placed the sleeping rooms. Next. That's the view from the entrance. We have also to use local design elements. The entrance is shadowed. It is covered with PV, and by producing renewable energy concurrently, it shadows the entrance of the room of that building, and so it's pre-cooled. Next. That's self-explained. It's the inner courtyard with water area and so on. Next. Nantong Towers, we had to design 3 high-rise buildings, a hotel, an office building, and a residential building. The curved form of the buildings brought a longer time for sun gaining at the south. So we brought the living building, we placed it at the south. The north, we placed the office building to reduce the cool load in the summer, and the office building is shadowed by the living building, by the residential building. So only by that design we could reduce the energy consumption by around 35%. Next.
Dear Ludwig, sorry for interrupting. Last 5 minutes, please. Can you plan that timing, please?
Oh, I thought the speakers could decide if they need more time. Okay, I will go on hurry. Here we can see modular building. We used containers for energy autark buildings in Mongolia. Next. That's a finished building from containers. It's totally energy autark. It works in the desert. Next. Also holiday chalets in south of China. Next. We had to shadow the building. That building has 2 skins. The main skin is shadowed by wood glass outside. Next. We also shadowed the south window. Next. That is the site of the largest passivhaus manufacturer in Harbin. Next. That was a model of the building. Here the manufactory, the magazine, the office building, in total around 35,000 square meters. Next. Here also the magazine, the manufactory, the office building. Next. Next. Also in that case is valid, long since the passivhaus is the highest standard in energy saving building, but it has to do, or it has also to reach other goals. Next. Next. For that building, the client decided for metal facade, which is totally recyclable. Next. We made a lot of workshops for the designers and also for the crafts to avoid construction mistakes. Next. We did not only do the design and the drawings, we also gave them pictures as exams to bet, so they could understand our design and our drawings better. Next. It's also an exam. Next. And the Chinese designers, they used our details and they had to implement our detailed design, and we corrected their mistakes and sent the corrected drawings back. Next. These are some exams of our drawings which were corrected by us. Next. Also a design workshop for the crafts to train them to build and to build correctly and to avoid construction mistakes. Next. That was an exam building. How have they to install windows? How could they avoid leakages in the airtight surface and so on. Next. That was a research project which we optimized. It was a result of architectural competition, and only by changing a little bit the window parts, we could save around $500,000. Next. The site was always clean and tidy. They worked very carefully. It's very important to sensitize and to motivate the crafts to do a very quality work which is very carefully neat and tidy. Next. The installation of the foundation of the building. Next. Here's also a proof for the carefully construction. Next. We developed by ourselves thermal bridge-free anchors for the facade. Next. Here you can also see the carefully construction implement. implementation. Next. The site was always clean and tidy. Very seldom I saw such clean site places and construction areas. Next. So the result of the blower door was very good, 0.2 instead of 0.6. It was the first test. It worked. They passed the blower door with the first test. Next. We also developed reinforced reinforced plastic materials, thermal bridge-free construction components for the metal facade. Next. It was a very ambitious achievement to install the sliding shutters for the office building, because we had 4 layers of shutters, and so a heavy weight, and we had to organize and to handle the thermal bridges. Next. The building under construction, the shadowing elements under construction. The next. Here you can see the manufacturer with the magazine, the office building, and also the gatehouse was realized as a passive house in Harbin, in the north of China, with average temperatures in the wintertime of -25 degrees. And when we visited the building after finished the construction in the first winter, always the doors were open, and the temperatures inside did not decrease less than +18 degrees in the case of outside temperatures of -25 degrees. Next. That's a picture of the factory. The office building here was under construction, and the gatehouse. Next. I think it's also a building in a high quality in aesthetics. Next. And it's also handleable. You can clean the facade very easy. Next. Next. During the process, as in that manufactory, they produce passive house windows. It is always clean, comparable to a hospital. And the client said to me, I learned from you because the construction was always very carefully neat and tidy. And that's what I learned. And now I will produce in the same way. Next.
Excuse me, Ludwig. We have completed our timing, but maybe 1 or 2 minutes extension.
Okay. I give speed. That was the Ceylan Europe competition with our students. Next. It was the first textile energy autark building worldwide. Next. It was built and designed by students. Next. Next. We implemented a zipper so the visitors can have a look into the construction. Next. Next. That was our up to now most ambitious project in China. The Siemens Center in Sino-German Eco Park in China. It was a German-Chinese government project. Next. That was the day of the opening ceremony. From the signing the contract to the opening ceremony, it was 2 years and 2 months. Next. Next. The auditorium. Next. And the foreign minister for foreign affairs, former minister for foreign affairs and vice chancellor Sigmar Gabriel visited that project, and he was very proud about the result. Next. Thanks so much. Sorry for taking the time.
Ludwig, thank you very much for your presentation. The title of your presentation was the biggest passive house project. So I had thought on it, and I had found an ironic feeling in the case of referring to its scale and being passive and being an environment friendly. But then in your presentation, we understood that it was a manufacturing building. So it's not a house. So maybe it's a kind of a problem in the case of translation from German to English, I guess. And we listened some passive house examples for different climates, from different climates and from different countries, from Dubai to Mongolia to China. And thank you very much for your presentation. I guess we have only 7-8 minutes rest for the question and answer session. Are there any questions? Yes. There is a question to Kirsten Henson. Can you please turn on your microphone? And I'm going to read the question. Are local products the key of the energy efficiency buildings? If you have to choose one option, zero energy buildings with no local products, or do not do zero energy buildings if you don't have local products, because of the embodied carbon is a big issue.
It's an interesting question. I think for us, the local product is more about supporting the capacity within the UK construction industry to continue to deliver as we fall out of the European Union, with issues associated with supply chain and the COVID. It's more about being able to supply our own market and specifying products that are less likely to be interrupted by these sort of economic and political instabilities. We have found that actually transportation, particularly where we're getting products within Europe, the transportation carbon is not necessarily the most significant element associated with the construction footprint, the life cycle. Maybe 3%, 4%. So if there is an energy efficient product that is manufactured in a different country, then I would say, by all means, if your sole focus is on carbon, the chances are it's probably better to take the energy efficient product, because transportation is not necessarily going to be a significant contributing factor to the overall carbon footprint of a building.
Thank you very much for your answer. I'm going to proceed to the second question, which is to Ludwig Rongen. I'm reading the question for you, Ludwig. Passive house is not just for housing as we see now. Ceylan factory is the best example. Why is this called passive house? Is this like a brand now? We are trying to explain it is not just for houses. What does PHI, I guess the question is about passive house, I guess, and you think about that.
What was the question? Sorry.
Why is this called passive house? Is this like a brand now?
Passive house, they call it passive house since more than 25 years. In 1991 in Germany, they thought about a passive house, about a house which could be warmed, or in which we could keep the warmness without active energy supply. Because of that, it's called passive house. A passive house, in theoretical, does not need any active energy. It's warmed and cooled by passive energy, by the energy of the people who live in that building, by the electric machines who give up warmness, by heat recovery, by sun gain, and so on. In my opinion, not only in my opinion, passive is not a good brand, because if you translate the word passive, it has worldwide negative image. Very often, when I'm invited as a speaker, they ask me, please do not translate the word passive house. And if you watch my presentation, I need only the German word passive house, and I do not translate it in English, but it's also, it's the same sound as passive house. But we should think about future buildings or zero energy buildings or nearly zero energy buildings, but passive is not a good image. But passive is a brand, especially in China. In China, passive stands for quality.
Thank you very much, Ludwig, for your answer. There is another question, and this question is a general question for everyone who wants to reply it. Please open your microphone and answer, please. Local products for passive houses are so limited in Turkey. How can we start? Should we wait for local products to develop and spread across the country? Europe is the closest bazaar to Turkey, but the zero energy building is not feasible due to the exchange rate. What is the best way to start?
I'm going to jump in there if I may.
Please.
As I hope you realised from my presentation, the product is not the place to start anyway. It's the design. We need to be looking at compact, efficient design, limiting the complexity of connections. There is nothing stopping designers in Turkey really challenging the way that their buildings look, the way that they believe their buildings will be constructed, to generate, you know, having proper shading to prevent excessive heat gain, having an efficient building form to ensure that you're not losing heat in the winter. All of these things are absolutely available. And there must be local construction products. We haven't worked in Turkey, so forgive me, but there must be local construction products that you can use. I wouldn't get stuck on passive house. You can still do low carbon buildings without having passive house certified products. We haven't, on the case study that I presented, we haven't focused on passive house products. We focused on proper building. I'm going to call it proper building design because it is the way that we should be designing buildings. We focused on efficient engineering, efficient structures, using existing materials, waste materials that are available to us. So, you know, please don't feel that you need something that, you know, your extremely low U value can be created by thick walls, more insulation. Perhaps you can't get a window that is really, really low, as we saw in Ambrose's presentation, the very, very good specifications of glazing products. But if you've got a massive south-facing glazing, that's a problem. You know, start there with fundamental low-carbon building design principles, and you'll go a long way towards net zero carbon.
Thank you very much, Kirsten. I completely agree with you. First of all, as we, the designers, need to understand the context well first and try to understand the opportunities and possibilities and the dynamics of the context. And designing is the first phase of this approach. I completely agree with you. Thank you. And another question to Ambrose Dodoo. Thanks to Mr. Dodoo for presentation. Will he share graphics soon? Your microphone is off, Mr. Dodoo.
I think I have sent my presentation, and it's okay to give it to people. So
okay.
It's okay.
Thank you very much. And the last question to Kirsten. I'm reading the question now. Can you compare the market of green construction materials to that of non-green construction materials in terms of cost efficiency?
Interesting question. And again, you know, this is purely focused. The question focuses on what is it going to cost me to buy that product, and we really shouldn't be just making that direct comparison when we're talking about sustainable buildings. But I'm going to answer the question in the sense that it's written. So at this moment in time, we do often see a small cost premium associated with green construction materials, but that's largely to do simply with the scale of adoption. And as we become, as clients start demanding more and more greener products, for example, insulation products are a great one. There's so many natural insulation products that we can use. The cost is going to come down simply because we get efficiencies of scale as we move away from traditional products. An interesting one, for example, with concrete, when we used to have coal-fired power stations in the UK, we only have 6 left now. It produces something called PFA, and it's great partial substitution for cement. Ambrose said why cement is so damaging from a carbon perspective. And actually, PFA was cheaper than cement. So the concrete, which had a 30% PFA substitution, was actually cheaper. Now we use GGBS from the steel industry, and actually it's probably at a par. So you can get a lower carbon concrete with GGBS substitution that you pay no more for. So it's really to do with the scale and increasing the scale and the demand for a product will see prices increase, but also where we're seeing products that are using waste materials. Often those are really comparable to a less sustainable option.
Thank you very much. It was a very extended answer, very good answer for the audience, I guess. I'm going to ask the last question because Kirsten already answered that question. So this question is coming to Professor Ambrose and Professor Ludwig, and I would like to ask to share your opinion in a few sentences, then we're going to close up the session. What is the best way to start? First, Mr. Professor Ludwig, please.
To do it with a pilot project. We all do not believe what we see, we believe what we experience by ourselves. All other things are religion. And I think if people make their own experience, then we can convince them. Realized projects, and I agree with Kirsten, very well-designed passive house is not a high-tech building. A well-designed passive house is a low-tech building. That's always valid.
Thank you very much. And may I ask your answer and opinion, Professor Ambrose?
I think I will start from where Kirsten, started, or from a view that we have to start with the design. And when we start with the design, we come to construction materials. I think we need government intervention, because if you look at the analysis we did, it shows that the real discount rate is very, very important. So, for instance, if you want people, to invest in green technology, green buildings, then there has to be like soft loans or loans with lower discount rate for people who are investing in this kind of technology. There has to be market intervention. You cannot leave the market to operate by itself, because if you look at the traditional materials, they are highly subsidized, by society. And as Kirsten said, the scale of adoption for those materials are quite high compared to, these green technologies we have today. So we need government intervention, but we have to start with the design.
Thank you very much. I think we all agree in that idea. So now we're in the end of our session. As the moderator, I really enjoyed and I really took a lot of notes during your presentations. It was fruitful and very beneficial. And also, I think the audiences had a lot of information from you. Thank you very much for your different approaches. Thank you very much for making this presentation real. And I would like to thank to all the organization committee of this forum. And I would like to say goodbye from Istanbul. Nice to see you, and hope to see you again once more. Bye-bye.
And thank you. Bye from London.
Thank you.